Have you ever had that specific moment of regret? You know the one?
Mm-hmm.
You start a quick coding project, maybe a little script to rename some photos, something for yourself.
Oh, I know this feeling well.
And you think, I'll be done by lunch.
The famous last words of, well, every developer, it's just a small script.
Right. But then lunch comes and goes. You decide to add a feature for a colleague.
Okay.
Then you realize it needs to run on Windows, not just your Mac.
Yeah.
And suddenly it's 3 weeks later, you're just drowning in bugs.
And you feel like you're trying to run through molasses.
Exactly. You're trying to run a marathon through molasses.
You are describing a very visceral, very specific, and unfortunately universal nightmare.
I am indeed. And today we are diving straight into that nightmare. We are talking about the tar pit.
It is the perfect metaphor for the profession, really.
So we're doing a deep dive into Class 4 of the software engineering curriculum. We have a heavy stack of reading notes today from two absolute giants.
Heavyweights.
Fred Brooks is the Mythical Man Month, specifically Chapter 1, and the Pragmatic Programmer, Chapter 8. Plus, we've got some lecture slides that cover everything from requirements to failure analysis.
And these aren't just textbooks, they're survival guides. Brooks wrote his book in the 70s, but the problems he describes, that feeling of being stuck.
Hasn't aged a day.
Not one.
That is what scared me the most reading this. The tech changes, the languages change, but the traps stay exactly the same.
Mm-hmm.
So our mission today is to figure out why projects get stuck in this tar pit, and more importantly, what can we do before we write a single line of code to stay on solid ground?
And that word before, that is the key. Once you're in the tar, it's usually too late. You need to map the terrain first.
Okay, so let's start with the image itself. Fred Brooks opens with this incredible analogy of the La Brea tar pits.
So vivid.
When I think of prehistoric extinction, I think of, meteors, big dramatic events.
Right, and that's the misconception about why software projects fail. In the tar pits, you don't see a T-Rex getting hit by a rock. You see a powerful beast that just stepped in something sticky. It struggles, gets another leg stuck, and then another.
It's not a catastrophe, it's an accumulation.
An accumulation of friction.
Yeah.
And in software, that tar, that stickiness, is complexity.
The dependencies, the interactions, the fact that changing one line here breaks three things over there.
It is slow, it's agonizing, and it kills projects more often than bad ideas do. Nobody sets out to build a bad system. They get stuck.
Brooks actually tries to quantify this. He has this grid in the notes that I found.
Yeah.
Well, really eliminating. He separates a program from a programming systems product.
This is maybe the single most important concept for a junior engineer to get. It explains why your homework is easy, but a real job is hard.
So it's a grid. Top left, you have the program.
Right. That's your garage project, the script you wrote for yourself.
It works on my machine. I know not to type ABC in the date field.
You just don't do that. You're the user and the author. Let's call the effort to build that 1x. It's our baseline.
Okay, 1x. But now I want to give it to my teammate. I want to turn it into a programming product.
So you move across the grid. Now you need documentation, you need testing because you can't stand over their shoulder.
You have to handle the fact that they will type ABC.
You have to. And Brooks estimates that's a 3x multiplier in effort.
Wow. Just to make it usable by someone else.
Just for that. But that's only moving horizontally. What if you go vertical? What if your program needs to talk to a database or an API?
It's part of a larger system, a programming system.
Correct. Now you're dealing with interfaces, things you don't control. If the API changes, does your code break? That is also a 3x multiplier.
So here's the math that it blew my mind. Clients don't want a script. They don't want just a product. They want a programming systems product.
They want the bottom right of the grid.
The part where the multipliers stack?
3 times 3.
9. A 9-time increase in complexity and effort compared to that simple garage program.
A 9x complexity multiplier. And that gap between the 1x we imagine and the 9x reality, that's the tar pit. That is where schedules go to die.
That sounds so miserable. So why do we do this? Brooks lists some joys of the craft, and I have to admit they really resonated with me.
It's creation, isn't it? Pure thought stuff. You build castles out of air.
And he calls it the pinball machine effect. Just watching the mechanisms work, it's fascinating. But he doesn't shy away from the woes.
No, he's very honest. The demand for perfection is just brutal. I mean, in most things, 99% is an A+.
Right. In software, if one character in a million is wrong,
the whole system crashes. A misplaced semicolon can bring down a bank.
Or even worse, bit rot. The world keeps moving around your code. New operating systems, new hardware. It's decaying before you even finish.
It requires a certain kind of resilience.
So let's pivot. We know the tar pit is there. How do we avoid it? This brings us to the pragmatic programmer and this whole idea of what to do before the project.
This is the shift from how do we code to what are we coding? Because so much complexity comes from not knowing what you're building.
The notes call this the requirements pit.
And that's the biggest myth in the industry, the idea that requirements are just lying around like rocks waiting to be gathered.
We even say requirements gathering.
As if it's a harvest. No, they're not rocks, they're fossils. They're buried deep under layers of assumptions and politics and just plain bad communication.
A lot of the time, the client doesn't even know what they really want.
Which leads to that great line from the notes.
Programming is therapy.
It's absolutely true. Your job is to be a therapist for their business process. You have to help them understand what they actually want.
There's that classic visual for this in the slides, the swing cartoon.
The tire swing, a legend.
For anyone who hasn't seen it, it's a series of panels. The first is how the customer explained it, and it's this complex ladder swing.
And then how the project leader understood it is a swing attached to the trunk of the tree so it can't even move.
It just goes on and on, how the programmer wrote it, how sales described it.
Which is always some kind of flying armchair.
And then the final panel, what the customer actually needed.
Yeah.
And it's just a tire hanging from a rope, a simple tire swing.
It's funny, but it's also incredibly painful because it shows how expensive that gap is. You just spent a 9x effort building the wrong thing.
To bridge that gap, the notes make a really critical distinction. Requirements versus policy. Can we break that down?
Yeah, this is so important. A requirement is an invariant, a fundamental truth. For example, we need to distinguish one employee from another. That's always true.
Okay, that's the goal.
A policy is how we choose to do that right now. For example, use a 5-digit ID number.
So the requirement is the what? The policy is the how.
Exactly, and policies change all the time. The notes use the Y2K bug as the ultimate example.
Oh, right. The Millennium Bug.
The requirement was the system needs to know the date. The policy in the 60s, to save memory, was store the year as 2 digits.
So 99 was 1999.
And developers treated that policy like it was a requirement. They hard-coded it. So when the policy expired, the code couldn't handle 00.
The time bomb went off.
It did. So programming therapy is digging past the policy. We do it this way. To find the requirement, what are we trying to achieve?
Okay, so we're therapists, we're digging for truth, but eventually we have to write it down. We need tools. The lecture slides walk through a toolkit for this.
Right, the tangible artifacts, the things you create so everyone can agree on what you're building.
Let's start with the use case. The slide highlights something called alternate courses of events.
And that is the most important part. Everyone plans for the happy path.
And everything just works perfectly.
User logs in, clicks buy, payment goes through. But the use case forces you to ask, what if the credit card is declined? What if the inventory hits 0 while they're clicking?
The edge cases.
That's where all the complexity hides. If you don't define the alternate courses, you're not designing a system. You're designing a wish.
Another tool is the data dictionary. This sounds incredibly boring, a glossary. Do we really need that?
I absolutely do. It saves lives. I mean, if I say user, and I mean a guest on the site, and you hear user and think a paid subscriber,
we're going to write completely incompatible code.
And it will blow up. The data dictionary forces everyone to speak the same language. It prevents that Tower of Babel collapse.
Then we have NFR's non-functional requirements.
The illialities. Usability, reliability, scalability.
These feel like the ghosts of a project. Clients forget to ask for them.
Oh, they always do. The slide lists things like access, security, capacity, and performance.
Like sub-second response time.
Perfect example. If you don't write that down, you might have a system that works but takes 10 seconds to load a page.
It's technically correct but completely unusable. A failure.
Exactly. NFRs define the quality of the system. You have to drag them out of the client during the therapy session.
Okay, there's one more tool in the slides that looks pretty intense.
Yeah?
FMEA. Failure mode and effects analysis.
I love FMEA. The pragmatic programmer calls this pragmatic paranoia.
So it's a spreadsheet. In the example, there's a masking tool to hide private data.
Right. So you list a step, run masking tool, then a column, potential failure mode.
And the example is unable to run.
Okay, what's the effect? Private data gets exposed. You rate the severity, let's say 9 out of 10.
High.
Very high. Then potential cause, why would it fail? Maybe the user not in proper directory.
And the last column is recommended action.
This is the payoff. Because you thought about this before you coded, you can now add a check. You can write code that verifies the directory first. You prevent the disaster.
So you're basically simulating the tar pit in a spreadsheet so you don't have to live through it.
You're finding the edges of the box. You're asking, how can this break, instead of assuming it won't? It's defensive thinking.
Speaking of things breaking, let's talk about scope. Because even with perfect requirements, there's always the temptation to add just one little thing.
The wafer-thin mint.
Yes. The Monty Python sketch. Mr. Creosote has eaten a massive meal. He's about to burst.
And the waiter offers him just one wafer-thin mint.
He eats it, and kaboom.
It's a grotesque but perfect metaphor for scope creep. Projects rarely fail from one huge bad decision.
They fail from feature bloat.
The accumulation of hundreds of just one small feature requests that weren't in the plan, and each one seems harmless, like a wafer-thin mint.
But remember the 9x multiplier. Each feature adds complexity, testing, maintenance, and eventually, the project just explodes.
And if you don't track those requests, you can't defend the schedule. You just look slow.
This brings us to agile. The notes make a great point. Agile is an adjective, not a noun.
Crucial distinction. You can't buy a box of Agile. It's not about having stand-up meetings.
So what is it?
It's how you do things. Small steps. Feedback loops. The notes say, work out where you are, take the smallest meaningful step forward, evaluate, repeat. It's about being agile, being responsive.
And that responsiveness depends on the team structure, which brings us to Conway's Law.
My favorite, coined in the 60s. It says that the design of a system will copy the communication structure of the organization that builds it.
Give me the classic example.
A compiler. If you have 4 isolated teams working on a compiler, you will get a 4-pass compiler. Guaranteed.
Because the teams don't talk to each other directly.
Right. Team A finishes their part and hands it off to Team B through a strict, formal interface. The software architecture literally mirrors the org chart.
So if you want an integrated system, you need an integrated team.
You do. If you try to build a fluid product with a siloed organization, you're fighting Conway's Law, and you will lose. The friction will show up in the code.
One way to force that integration is pair programming. That's 2 developers, 1 computer.
1 keyboard. One person is the driver, typing. The other is the navigator, thinking about the bigger picture.
That sounds intense, having someone watch me type.
That's part of it. It's good peer pressure. You're less likely to cut corners or write sloppy code when your colleague is right there.
It keeps the quality high.
And it spreads knowledge. It reinforces that software is a human activity. It's all about communication.
Okay, I want to touch on the specific instructions for the students in this class. There are slides just for the discussion leaders. Their job isn't just to stand up and summarize the chapter, is it?
No, and that's a common trap. Your job is to facilitate. You need to lead a discussion. Do we agree with this? Does this apply to our projects?
And there's a specific deliverable.
Yes, the wiki. The leader has to update the reading discussion notes page. They capture the overview, but more importantly, the decisions and the open items. What did we actually learn as a group?
There was also a slide mentioned the periodic table of DevOps tools.
That's a bit of a visual shock tactic. It shows the sheer number of tools out there. Jenkins, Docker, Git, Kubernetes. It's a reminder of that complex programming systems product world.
Right. You're not just writing code.
You're navigating a huge landscape of tools.
And finally, let's look at the homework.
For Wednesday, January 28th, the reading is The Pragmatic Programmer, The Postface, and Chapter 1.
And the syllabus notes that readings won't always have slides.
A life lesson right there. Don't wait for the PowerPoint. Go to the source material.
So, to wrap this all up, we've covered the tar pit, that 9x multiplier. We've talked about therapy to get to real requirements. We've looked at the toolkit to simulate failure before it happens.
It's a lot, but this is the foundation. If you skip this part, you're just hoping for the best, and hope is not an engineering strategy.
Before we sign off, I want to leave our listeners with one last thought from the notes. The concept of impossible puzzles.
A great way to end?
It's the 9-dot puzzle. You have 9 dots in a square, and you have to connect them with 4 straight lines without lifting your pen.
And if you try to stay inside the square formed by the dots, it's impossible.
The only way to solve it is to draw the lines outside the imaginary box.
And that's the key. We always hear, think outside the box. But the notes say the box doesn't even exist.
The constraint was in your head. Nobody said you had to stay within the dots.
You just assume.
So here's the question for you to mull over. In your current work or your studies, Are you struggling with a problem because you're following a rule that isn't actually there?
Are you treating a temporary policy like an immovable requirement? Find the real edges of the box. They're usually much further out than you think.
Thanks for diving in with us. We'll catch you next time.
Happy coding.